Okay, in this short video, I'm just going to talk briefly about what matrices are and a little bit about how we describe them before, in a later video, getting onto using matrices. So basically, matrices are essentially just tables of numbers. They can be other things as well, but for our purposes, they'll be tables of numbers, kind of like this one that we've got here as an example. Now, they come along with some associated mathematical rules, which we'll look at in other videos as well. Okay. And that's kind of what sets them aside from just regular old tables of numbers. So first of all, just in terms of describing things, we describe matrices in terms of their size. And the size of a matrix is just its number of rows and its number of columns. So this example we have here is referred to as a 3x2 matrix in terms of its size. And that's because it has 3 rows and 2 columns. So you can see 1 row, 2 rows, 3 rows, and then 1 column and 2 columns, so 3x2. And it's always in that order, rows first, columns second. We'll generally, when we're writing a matrix, we give it a letter to represent it. Usually it's a capital, and we use this double underline to represent that it's a matrix, as opposed to just a regular old number. Now, the things inside the matrix, the numbers in this case, are referred to as elements of the matrix. And we refer to them using the lowercase version of the letter that's used for the matrix. And these numbers here tell us which row and column we're talking about. So 1, 1 means I'm talking about row 1, column 1, which is just the number 1. 1, 2 means I'm talking about row 1 and column 2, which is number 4. A22 then would be row 2, column 2, which is a 9. And so on for the rest of them as well. So that's how we refer to elements. We can have equality of matrices, and matrices are equal when they have the same size. So they must be identical in size, the same number of rows and the same number of columns. And once you've got that, they also need to have exactly corresponding elements. So each of the elements must be exactly the same across the two matrices. So the first row, first column in one matrix must be the same as the first row, first column in the other matrix, and so on for all of the elements in order for them to be equal. So another little bit is to talk about types of matrices. This is useful for various purposes, but sometimes we'll be trying to find matrices of different types, so it's good to have names for them. The first one is the column matrix. Now, column matrix, here, B is an example. It's just a matrix that has just one column. So you can see there just the one column. And of course, we also then have a row matrix, which is a matrix made up of just one row. The next one along is a square matrix. So there's an example there, matrix S. And a square, you might guess this one, has the same number of rows as it has columns. So this particular example has 1, 2, 3 rows and 1, 2, 3 columns. So it's a 3x3 matrix. It's a square matrix. We can have 2x2s, 4x4s, 10x10s, and so on. As long as the same number of rows and columns occur, we'll call it a square matrix. Diagonal matrix is a matrix that only has non-zeros on what we call its diagonal elements. So the diagonal elements are A11, A22, A33, and so on. So row 1, column 1, row 2, column 2, row 3, column 3, and so on, depending on what the size of the matrix is. So as long as there's no non-zeros outside of that diagonal line, we'll call it a diagonal. There could be zeros on the diagonal, that's fine, but we just don't want any non-zeros outside of it. Sort of similar kind of thing is the upper triangular and lower triangular matrices. So here we've got U as an example of an upper triangular matrix. Now you can see probably why that is. The upper triangle of elements are the only ones that can be non-zero in an upper triangular matrix. Everything under the diagonal must be 0. Again, we can have zeros in the upper triangular part as long as we don't have non-zeros below the diagonal. In the reverse situation, a lower triangular matrix like the example L here, its non-zero elements only occur on or below the diagonal. Everything else above the diagonal must be zeros. Now, one last thing you might have heard me use the word matrices, and you can see it up here, types of matrices. That's our correct plural word for matrix. Okay, so matrix refers to one of these things, and matrices for more than one. We don't say matrices or matrices. Okay, so matrix is one, matrices for multiple, more than one. Okay, so that's it for just this first little intro video on matrices. In some later videos, we'll look at what we can do with them mathematically in terms of operations, and also how we use them in context to do things like solve equations.